So we are going to continue our discussion of the infinite square well. Remember that we found the energies and we found also the solutions, the wave functions corresponding to each one of those energies. And what were, how did we write that? Well, we had the square root of 2 of A. And so this is came from the normalization of the wave function. And then we have the sinusoidal part with this K, with this index N. So this K, N is what gave us the energies, no? X. Okay, what is this K? N is N pi over A. Okay, so let me rewrite this function using that. So square root of 2 over A, sine of N pi x over A. This is the solution. And what we are going to do now is to discuss some properties of this solution. Okay, so let's start with an easy one. Let's start by looking if we had to make plots of these functions. So let's start with N1. When N is 1, that's the lowest energy, we say that this is the ground state. And what is the wave function? We'll have just the sine of pi x over A. So this is what we have to draw. So how do we draw? Now is a sine. So the drawing for the psi 1, this, let me call, this is 0, and this is A. Okay, so we start at 0. The wave function has to be 0 because that's where the wall is. Remember, our potential has this wall, this enormous infinite barrier at 0. So the wave function there starts at 0, sine of x at 0, 0. Then we go with the cosine until we reach A. A is the other wall, the infinite barrier there. We go back to 0. So this is the drawing of this sinusoidal function. Very good. Ground state. Let's now make the plot for N2. So N2 will have now the sine of 2 pi x over A, right? So how are we going to make this plot? This is A, this is 0. We start at 0, but careful. Now when x is A over 2, at this point here, we have sine of pi. Okay, so we are going to go up, and then here we get 0, and then beyond this point, it's negative. So this is A over 2. And the last one, for 3, we'll draw the sine of 3 pi x over A. And here there are 2 intermediate important points. So let's try to make them here. This is point A. This is A over 2, but somewhere here, we have, now I have, well, my drawing may not be perfect in the scale, but the important points are x at A over 3, and then x at 2A over 3 are points where this function, this sign will be 0. So we go, here is my A over 3, so it becomes 0, then we go negative, and then here there is the 2A over 3, and then finally we go back. Now, so this is a sketch, not the best one, but this is A over 3, and this is 2A over 3, when the wave function becomes 0. Okay, so this is the first discussion. Now we made these plots, and the first property that we can then talk about with respect to the solution is the ground state is even with respect to this center, meaning the function to the left or to the right of this point is like a mirror. It's both positive. Now here, in the next case, if you look at the solution to the left and to the right, they are the opposite. One is positive, the other one is negative. Here we have an odd function. And in the last case, what we have is exactly the same. The left and the right is like this reflection, no, is again even. And so this is to say that if we go ground state even, first excited odd, then even, then odd, then even, then odd. We go on alternating like that. Another property, what do we see? In the ground state, in the ground state, we don't have any nodes. We just have the edges here of the wave function. So no node. When we go one step up, when we go to the first excited state, we get one node. When we go two steps now above the first excited, if we go to the second excited state, we get now two nodes. So every time we go one step up in energy, we get one more node. Okay, so this is one more node. This is the second property. So these are easier ones. Now, the very, very, very important property is that these solutions, these functions, they are orthogonal. Now, this is super important. We'll be using and talking about this throughout this course. And what does it mean to be orthogonal? It means that if I pick two of those solutions with different index m, and put here the conjugate, and pick the other one n, if this m and n are not equal, this is 0. This is what means to be orthogonal. Let's prove that. So if m is different from n, let's prove that this integral is 0. Well, so let's pick our wave function, now the solutions that we had. So for this one, we have the square root of 2 over a. Now the sine of m pi x over a. For this other one, we have again that square root, and now sine of n pi x e. All right, so let me rewrite this integral. We have the square root appearing twice, so here it is that ratio. We have to do the integral. We are thinking about the infinite square well. The part where it's only between 0 and a. And then we have sine m pi x over a, sine n pi x over a dx. And we want to show that this is 0. So you see, to solve this integral, we need to know how to deal with trigonometric functions. So that's why I was telling you it's very important to remember how to deal with trigonometric functions. So what is it that we are going to need here? Let me remind you of some properties, okay, some relations, some trigonometric relations. Suppose we have cosine of a minus b. Do you remember how you can write that? You can write cosine of a, cosine of b, plus sine of a, sine of b. You must have learned this before. Well, how about if I put cosine of a plus b? This is cosine of a, cosine of b, now minus sine of a, sine of b. Why am I doing this? Because in our integral, we have two signs. And I don't know what is this integral. I know the integral of one sine or of just one cosine. So I'm trying to find a way to rewrite this product in terms of a single cosine or a single sine. So that's why I am coming to this relationship, because look, if I do the first one minus this one and sum the two, what do I have? Cosine of a minus b minus cosine of a plus b is equal to what? These two cancel, is equal to 2 sine a sine b. So this is a very good relation for someone who is trying to solve this integral. how can I write this integral? I can write that integral in terms of just 2 cosines. So let me do it here with you. 2 over a. Now, inside the integral, I'm going to put cosine of a minus b. Well, a minus b in our case is, this is my a and this is my b. Okay, so I'm going to write it as cosine of m minus n, and the rest is all things that they have in common. And so is that a that both terms have, the pi and x. Okay, so if something is not clear, write down yourself. Be sure that you understand all of these steps. Then I'm going to put minus and now this sum of the sum of the terms. So it's going to be cosine. Now the sum of the terms inside those signs, what is that? M plus n over a and the pi x, that is both of them. Okay? And don't forget, there is a factor of 2 in this story. So let me divide all this by 2. Well, 2 here and 2 here cancel. Okay, so we have now to solve this integral, but this is easy. We know how to solve an integral with just 1 cosine, correct? So then let's solve it. The first integral is going to be a sine, right? So sine of m minus n pi x over a. Well, divided by what? By that m minus n pi x over a. So this over a, I can put it up here. The next one, we have minus, and then we have the sine of m plus n pi x a divided by m plus n pi x divided by a. So I can put this a here. And this is what are the edges of my integral. 0 to a, 0 to a. Okay, so let's check little things. There is an a in front of all of them, and we have this a, so cancel. All right, now what's, oops, sorry, I made a bad mistake here. There is no x in this story, yeah? So this is just, I should just look at this part, no? To put it in the denominator. Okay, good. So now what do we do? Well, let's look at these extremes. Now, very important. Sine, doesn't matter what we have. Doesn't matter what is the value of this m and n. We know that m and n is a number 1, 2, 3, 4, 5. So it's going to be a positive integer. Okay, so m minus n pi a, when x is a, which is this top here, when x is a, is what? Doesn't matter which m or n we have. This is a positive integer. This, oops, this a cancel. So we have sine of some multiple of pi. We know very well that this is 0. Okay. Same thing for the other side. If you look at this other term, m plus n pi, when x is a, what do we have? Those a's cancel. It's going to be sine of a multiple of pi. This is here. Okay, so this is to talk about this a and this a. How about 0? Well, sine of 0 is 0. Okay, so all that to finally come up with the answer that we were after. This whole thing is 0. And so the answer, we finally proved that if we have two functions, the first one conjugate to the next one itself, this is going to be 0 if m is different from n. Okay, well, and how about if m is equal to n? If m is equal to n, we are back to normalization. Okay, and so when m is equal to n. So how can I write this whole thing in with a symbol that gives me both? We can say that this integral of n and m and n functions is equal to the delta. Yeah? So this, what does this Kronecker delta tells us? What is the Kronecker delta? The Kronecker delta is 0 when m is different from n, 1 if m is equal to n. Okay, so this is a short way to say that the functions are not just orthogonal, they are in fact orthonormal. Okay, they are orthogonal, no? When m and n, this gives us 0, but they also normalize. No? This integral is very good. So this is the very, very important third property, orthogonality, and more than that, these solutions are orthonormal. Let's go now to one more very, very important property, which is complete. The solutions are complete. What does that mean? It means that you can pick any function of x, and you can write this function of x as a sum, as a linear combination of our solutions. Okay, where this n goes from 1 to infinity. What are our solutions? Well, sinusoidal functions, right? We had that sine of n pi x over a. So what we are saying here is that any function can be written as the sum of sines. This way of writing the function is known, some of you may have heard about it, as Fourier series. So any function can be written as a sum of sinusoidal functions. This is a property that you may have heard about, but if you have not, here it is. You can write any function in terms of sum of sines or cosines. Okay, so our solutions are complete. And then if we had to find these coefficients, how can we do? How can we find these coefficients that will allow us to write any function in terms of this sum? Here comes a trick. What we are going to do is the following. Let me multiply the left and the right side by psi, by psi of m conjugate. Okay. First thing, I'm multiplying the left and the right side by this psi of m x. All right. And then now, in addition to that, do an integral of the left and the right side. See, I kept the CNs outside the integral because these are just constants. Okay. This is a very smart trick. Why is that? We just learned that this is the Kronecker delta, that this integral is 0 when m is different from n, or is 1 when m and n are the same. That's normalization. So this is very nice because we just solved the integral. Okay, so what do we have now? We found that that whole integral is gone. I have Cn of the Mn. Okay. So what this Kronecker delta tells us is that that integral is 0 if m is different from n. So in this whole sum, whenever n is different from m, we just get 0. So the only thing that survives here is when n is equal to m. So the only thing that survives from this sum is the Cm. All that to say that Cm, those Cm's, those coefficients that we have here, can be obtained by solving this integral. Okay, well, so this is the result, but if you prefer, we can write the same thing in terms of Cn. The name that we give to the index could be N, M, P, doesn't matter. The important thing is I found this relation, so I can write now it in terms of N. Okay, so excellent result. I know how to find these Cn's. So I know by doing this calculation, I know that I can write any function as a sum of those solutions from that we got. What do I have to do? I find the Cn's from this integral, put them here, and I got my function. Why is this so important? Why should we be really happy about that? Let's remember our recipe. The recipe that we said. How are we going to find the whole wave function, the solution for the time-dependent Schrödinger's equation? We said, oh, first thing, we are going to solve the time-independent Schrödinger's equation. We are going to find all of the energies and the corresponding functions. Okay, well, thinking about what we just did now in this section was to find the solutions for the infinite square well. Okay, so this we have. So in our process to obtain the whole solution, the whole wave function, we already did the first step. The second step, we said, well, we need to have the initial state. Well, what is this initial state? A function of x. We need to have this initial state, and then with this initial state, we'll write this initial state in terms of those solutions. Okay, so when we introduce this, you might have wondered, oh, how am I going to do that? They give me this initial state, but how am I going to write this sum? Now you know. Now we know how we are going to obtain this Cn's from here. Okay, so in the particular case of our the infinite square well, how are we going to do that? How are we going to find these Cn's? We are going to put the psi n in the particular case. Let me just rewrite this. In the particular case of the infinite square well, this is going to be that solution that we obtained. Okay, and here where are we going to put the function? This function, which is our initial state that someone will have to give us. And then once we are able to write this initial state in terms of our solutions, we are done. We can find the total solution for the time-dependent Schrödinger's equation just by attaching to this each element of this sum the time-dependent part, the part that depends on time. What is that? That exponential with the energies h bar, the energy that we obtained by solving Schrödinger's equation, the time independent. Okay, so did you understand the procedure? So in our case, we already did everything. Now we have the solutions from the time independent Schrödinger's equation. So we have that. Number two, well, it will depend on the problem. They will give us the initial state. We can write that in terms of those solutions, where the CNs we know how to obtain through this integral. And then finally, after all that, we have the whole solution for the time-dependent Schrödinger's equation with those phases, with these energies that we obtain. Okay, so in our particular case, for the infinite square well, what is going to be the solution, this complete solution? It will be a sum of these components. This will depend on the initial state. Okay, so let me repeat this discussion. This we are going to obtain through the initial state, through that integral that will give us those CNs. Then comes our solutions, those functions we have is sine n pi x over a. So this we have. And then comes the part with the energies. The energy we also have, we obtained. So it's n square, pi square, h bar square, divided by 2ma square. All that multiplied by time divided by h bar. H bar in the denominator, we also have in the numerator, so we can get rid of this. And this goes from n1 to infinity. That's the solution. Okay, so all that we need to do now, all that we need is give me this. So then we can find this final answer. And now we'll be solving problems where this is given to us. And so we can find the total wave function. Okay, so this is the end